Let's go ahead and talk about lesson 29. It is, as I said, it is a short lesson, so we can have some time to look at test questions maybe, go start homework, whatever we need to. But we are talking about something called differentials today. And you'll notice we're talking about Newton and Leibniz? I can't remember how to say his name. It just flew out of my brain. But Sir Isaac Newton and I forget, Gottfried Wilhelm Leibniz. Okay, so an Englishman and a German. However you want to pronounce those, okay? They are both credited with inventing calculus, but totally independent of each other. Like each in their own countries, each doing their own thing, creating calculus. Okay? So they're both credited with it. Now, so what this takes us to is that they had different ways of designating the derivative. So we've done a little bit with derivatives, right? We'll sometimes use the prime notation, like f prime of x or y prime or something like that. I sometimes use the dy dx, right? When I first introduced derivatives, I said there's this way, this way, this way. I showed you a whole bunch of different options, right? And the difference comes from who you're talking to. Okay, so for Newton, he used, actually at the time, he used a dot over. And so he used, I put a dot over that y, and he called it y dot. And that's what he used for the derivative. Now, over the years, it's changed to what we use, which is the prime. Most people tell by looking.
Really, Carly? You didn't even attempt to pull the door?
I pulled it.
Oh, I didn't hear it.
I didn't pull it very hard. I just went like that.
Well, it's unlocked.
It wasn't unlocked.
Yeah, well,
It wasn't.
The class is so very disappointed. They were expecting just a big yank. And
Yeah, like really?
Surprise.
Come on.
You gonna go and try again?
no, I want to teach. So Newton, when he invented calculus, he talked about derivatives. He used y dot, which over the years has become what we call y prime. Okay? Leibniz, when he did derivative, he used dy over dx, which you've also seen me use, right? I guess I'll put a y prime here. But the dy dx is what he used. And the idea of dy dx, first of all, it's what we often call differentials. And what we'll look at a little bit today is that the dy dx, it's a fraction. It's dy over dx. And you can treat it like a fraction, where the dy and the dx can be moved around independently. And that's the idea of differentials. So notice it says there to get rid of the dx, he simply multiplied it to the other side to leave dy. And that's the notation we're working with today. So, definition of a differential. That's what I was trying to say. I am just very tongue-tied today. And what you'll hear, another phrase for when we take the derivative is differentiation. So when we differentiate something, we are taking the derivative. That goes back to the idea of differentials. Now, so let y of x be a function that can be differentiated. So let y equals f of x be a function that you can take the derivative of. That's what that's saying. The differential of x, denoted as dx, is any non-zero real number. Okay? The differential of y, denoted by dy, is given by dy equals f prime of x dx. So that's a little bit what we're going to look at. Basically, I just want to kind of show you the idea of derivatives and how we can separate the fractions. Okay, we'll use them more as the year goes on for other things, but it's just kind of the introduction right now. Sorry, I'm looking at my notes. I guess before I go on, to kind of show you where this dy equals f prime f of x dx comes from, if I start with Guess I'll do this first. Y equals f of x. Okay. How can we write the derivative of y if we're using Leibniz's form? Leibniz. I can't remember how to say his name. That's going to bug me. dy dx, right? So the derivative of y can be written as dy dx. F of x, how do we write that? You write f prime of x, right? Kind of like it used to be the dot, but it's now the prime. If you think of a fraction, how do you solve this equation for dy? Yeah, if it's dy divided by dx, to get rid of the dx, you multiply by dx. If you multiply one side by dx, multiply the other side by dx. So the idea that dx's cancel, and dy is equal to f prime of x times dx, which is exactly what you see right up above there. Okay, that's how that comes about. The fact that, again, it's a fraction, you can separate it into pieces. There's a couple different ways we can think about this, but it says let y equals 3x to negative 2 plus 2x squared plus 1, find dy. One option is to just take the derivative as we would normally try to. So the derivative of y, how can I write that in the differential form? dy dx. Derivative of 3x to the negative 2. Negative 6x to the negative 3. Derivative of 2x squared? 4x. Derivative of 1. Okay, nothing. Now, this question specifically asked us to find dy. How do I find dy? 2 times by dx. If I multiply the left by dx, multiply the right by dx. A couple of different ways we can write this. One option is if you just write it times dx at the end, that would be putting the whole thing in parentheses. So negative 6x to the negative third plus 4x times dx. That would be one way to write it. Another way to write it is to actually distribute that dx. Again, it's just like a typical number variable. So if I distribute that dx, dy is equal to negative 6x to the negative third dx plus 4x times dx is 4x dx. I have this one boxed, and so I'm guessing that's the type of answers that they will show in the book today. Okay, but to me, these are both solved for dy, right? As long as you have the parentheses on this previous one, they're both solved, they're both there. Excuse me. I feel like at the point we're at right now, I like kind of taking the derivative of dy dx and then solving for dy. Okay. However, as you understand this more, if we're doing differentials and you want to, okay, the derivative of y is dy, because it's, so the derivative of x is at negative 6x to the negative third with respect to x, so dx. Derivative of 2x squared, 4x dx. In other words, if you're always tacking on the differential with whatever variable you're differentiating, that's a way to do this as well. Does that make sense what I said? Okay. Again, for the beginner step, I like kind of showing this because I want you to be able to see, okay, this is where it came from. So example 2. Let's y equals sine x plus cosine x. Find dy. So, derivative of y? dy dx. Derivative of sine x? Derivative of cosine x? So minus sine x. What do we do here to solve for dy? Multiply by dx. So dy is equal to the quantity cosine x minus sine x times dx. Or if we distribute, dy is equal to cosine x dx minus sine x dx. Okay? And again, you could, if you're asked to use differentials, derivative of y is dy. Because derivative of y is essentially 1, right? So it's 1 dy. Derivative of sine x, cosine x dx. Derivative of cosine x, negative sine x dx. So you're always tacking on with respect to whatever variable it was. Any questions there?